The CJ1000A was never expected to shake anyone in the West. Yet the latest test results from China's new engine landed on the desks of analysts in Europe and the United States, and the reaction inside Boeing and Airbus's circles was anything but calm. Because this is not a simple test run, it is the first clear sign that China's engine project may be further along than many believed. China could build the C919, but it could not control the most important part of the aircraft, the engine. Every C919 flying today depends on the LEAP-1C, a joint GE and Safran engine built in the United States and Europe. And as long as that remained true, one export license could stop the whole program. This was not a theory. It already happened. In 2020, Washington briefly weighed blocking LEAP deliveries. In 2025, the United States paused export approvals again, and the effect was immediate. C919 output slowed. Deliveries slipped. Comac had to cut its own yearly target by 2/3. Airlines that had lined up early orders suddenly had to wait. That moment exposed the weak point everyone in China already knew about. The C919 looked ready for the world, yet it could still be grounded by a decision made outside the country. And with more than 9,500 new aircraft expected to be needed inside China over the next 20 years, the stakes kept rising. This is why the CJ1000A matters. Before China could compete with Boeing or Airbus, it first had to break free from the only part of the plane it did not control. And the challenge was huge. No country has built a modern high-bypass turbofan from scratch in decades. The engineering, the materials, the testing hours, the failure cycles, the certification work. It is one of the hardest projects any industry can attempt. But China had no choice. If the C919 was ever going to stand on its own, it needed a homegrown engine that could match the thrust of the LEAP, survive the same temperatures, and deliver enough reliability to convince airlines it was safe to fly. The push for the CJ1000A began long before the sanctions hit. But after 2025, it changed from a long-term research plan into a national priority. And that is the moment the CJ1000A stopped being an experiment and became the center of China's entire aviation strategy. The plan to build a homegrown engine did not begin with sudden pressure from abroad. China started laying the groundwork more than a decade earlier, when engineers at AECC and ACE were tasked with building something the country had never succeeded at before, a high-bypass turbofan in the same class as Western engines that power the A320neo and 737 MAX. In 2011, a model of the CJ1000A appeared at the Beijing Air Show. Years later, in 2017, the first full demonstrator engine was assembled. That unit was not meant to power an aircraft. It existed to answer one question. Could China build a core capable of reaching the speeds and temperatures needed for commercial flight? Engineers spent months running that core under controlled conditions. Then in 2018, the CJ1000A spun up in a Shanghai test cell and hit full core speed for the first time. It was a milestone that showed the program was moving from theory to hardware. But building a working engine is not the same as building a commercial one. The next steps were slower, harder, and required thousands of hours of tests. Between 2019 and 2020, the program expanded into a wider set of trials. Ground runs pushed the engine through extreme cold, high heat, fast throttle changes, and mechanical loads. Bird strike tests were carried out. At the same time, China prepared plans for a flying testbed using a large military transport to carry a single CJ1000 on one wing. That setup would allow engineers to collect real flight data without risking a passenger aircraft. By 2023, the moment finally arrived. Photos appeared online showing a Xi'an Y-20 with one of its engines replaced by a CJ1000A. This was the phase that determines whether a new engine can handle real altitude, real vibration, and real stress. Most engines fail early in this stage. They run hot. They lose stability. They reveal flaws that need years to fix. But reports from inside the program said the opposite. The engine handled full thrust without major issues. It responded cleanly to throttle changes. And internally, Chinese officials said it was performing better than their most optimistic expectations. Still, the complexity of the project kept rising. After the first flight hours, engineers had to rip the engine apart, check wear patterns, replace parts, and run the whole cycle again. Over and over. Each round produced new data. Each fix brought the engine closer to the level needed for verification flights on the C919. Even with solid progress, the CJ1000A was not catching up in every area. Western engines still hold a strong lead in advanced materials. The LEAP uses ceramic matrix composites and higher temperature limits. The Pratt GTF has a geared drive that boosts efficiency. China is not matching those technologies yet. But the CJ1000A does not need to win a race in efficiency. It only needs to be strong enough to take the place of an engine that can be paused by a political decision. And by the time the engine reached consistent flight testing in 2024 and 2025, it was clear that China had crossed a line many believed it would struggle to reach. The most important phase of any new engine program is the jump from controlled ground tests to real flight hours. On the ground, engineers can shape the environment. In the air, the engine has to survive whatever the sky sends at it. And during the 2023 to 2025 test campaigns, the CJ1000A crossed several markers that surprised even analysts who have followed the program for years. The first sign came from the Y-20 test flights. This aircraft carried the CJ1000A in place of one standard engine while keeping the other three original engines unchanged. That meant the test crew had a safety margin while still putting the new engine through real altitude and real load cycles. In those flights, observers noted stable operation, smooth thrust changes, and no signs of the early stage problems that often show up in young turbofan programs. Then came the endurance runs. Report from Chinese sources described long test cycles at high power without major temperature spikes. Separate checks after these runs found where levels that were lower than early models had predicted. One former deputy manager at Comac said the engine was performing better than his most optimistic expectations. Coming from a veteran who had watched the C919 struggle through delays, that statement caught attention. Ground test continued in parallel. The engine was pushed through heat up to about 50 degrees and cold near -40. These steps are required for any engine that aims to reach commercial service, and each one reduces the chances of a late-stage failure that can set a program back by years. None of this means the engine is ready for airline operations. It needs far more hours, more stripped-down inspections, and more repeat cycles to prove long-term reliability. But the key shift is this: the CJ1000A is now past the early risk zone where most engines break down or show fatal flaws. This is where the mood changed in Western analysis. For years, the assumption was that China would run into hidden issues that would delay the engine far beyond its political timeline. The test data now suggests the opposite. The CJ1000A may not match the efficiency or materials of the LEAP, but it works. It flies, and it keeps improving. For Boeing and Airbus, that is the real concern. Not because the engine will beat their own models, but it puts Comac in an even stronger position to challenge the ongoing duopoly. And China has reached a stage many expected would take far longer. To understand why the new test results caused a stir, you need to see where the CJ1000A sits next to the engines that rule the single-aisle world. The LEAP from CFM, the PW1100G from Pratt & Whitney, and the older but legendary CFM56 still define the standards for modern narrow-body jets. Each of them took years of failures, redesigns, and hard lessons to reach their current status. When you line up the numbers and the performance reports, a clear picture forms of where the engine stands and why the latest tests matter. Start with the LEAP 1C, the engine that currently powers the C919. This model uses advanced cooling, composite fan blades, and ceramic materials that let it run hotter and cut fuel burn. In pure efficiency, the LEAP still has an edge. It has more flying hours, more data, and years of refinement that China cannot skip. But thrust is not the issue. The CJ1000A produces the right level of power for the C919. Its size and general architecture are in the same class. And while it lacks some of the advanced materials, the flight data suggests its core is stable at the required power levels. In other words, it meets the basic performance zone needed for commercial use. Against the PW1100G, the story shifts. Pratt's geared turbofan reaches strong efficiency numbers, but it also ran into early reliability trouble. Bearing wear, high vibration, and gearbox failures grounded aircraft and forced fixes across global fleets. The CJ1000A is simpler in design. It does not match the same fuel burn, but it avoids the risk of a complex gear system, which gives it a more predictable early learning curve. Then there is the CFM56, an older engine but one of the most proven in aviation history. Nothing today competes with its record for reliability. The CJ1000A is not trying to beat that legacy, but the technical gap is smaller here than between it and the latest LEAP variants. Many analysts view the CJ1000A as closer to a late-generation CFM56 in maturity and materials, which is more than enough for domestic routes. When you put all this together, the threat becomes clear. China does not need to build the best engine in the world. It only needs to build one that works well enough to replace the LEAP on Chinese aircrafts. And once that happens, the single biggest point of outside control over the C919 disappears. This is why the new test results matter. They show the CJ1000A is not stuck in the early stages. It is moving through the same steps that once made the LEAP and the PW1100G leaders in their class, only at a pace that few expected. The real turning point for the CJ1000A did not come from a test cell or flight deck. It came from a decision made thousands of kilometers away. In late May 2025, the United States paused export approvals for the LEAP-1C and other key aviation parts bound for China. It was framed as a response to trade friction, but the effect on Comac was immediate and severe. Within days, C919 production slowed. Shipments that airlines were waiting for simply stopped. Assembly lines that had been planning to push towards higher output were forced to sit idle. Comac went from ambitious delivery targets to a quiet cut in numbers. Internal filings showed the drop clearly. Instead of delivering more than 30 aircraft, the company had to reduce the target to just 25. For airlines, the pause caused ripple effects across fleet plans. Routes that were supposed to introduce new aircraft were pushed back. Pilots trained on the C919 had to wait longer for new frames. And observers outside China read the situation as a reminder of something deeper. This was not a supply issue. It was a lever that could be pulled anytime. The pause lasted weeks, not months. By early July, approvals were restored and GE could ship LEAP engines again. But the damage had already been done. The event showed how fragile the C919 still was under the surface. All the progress, all the orders, all the work going into production could still be halted by a single decision that China could not control. Inside China's aviation circles, the message was clear. As long as the C919 depended on foreign engines, the country's flagship jet could be slowed, shaped, or blocked by outside pressure. It was not only a commercial risk, it was a strategic one, and it raised the stakes for the CJ1000A more than any test result ever could. This is why the new flight data carried so much weight. It suggested that China was closer to removing the last major point of outside influence on its civil aviation plans. The export shock did not just slow the C919. It turned the CJ1000A from a long-term goal into the core of China's entire strategy. If the CJ1000A reaches full service, the landscape of global aviation shifts in a way that Boeing and Airbus have tried to avoid for years. It would not happen overnight. Certification, reliability trials, and long-term endurance tests still stand between the engine and the first commercial flight. But once it crosses that line, the balance of control changes. For China, the benefits are direct. The C919 becomes sanction-resistant. The country can scale production without waiting for foreign export decisions. Factories in Shanghai and Xi'an can run at full pace, and Comac can finally chase its long-term targets of reaching 100 to 200 aircraft per year. That would give China a real foothold in the narrow-body market, at least inside its own borders and in regions open to Chinese certification. It also opens the door to exports. Countries in Southeast Asia, the Middle East, Africa, and parts of Central Asia could buy the C919 with a Chinese engine and avoid entanglement with Western suppliers. Maintenance, parts, and servicing could all come from China. That kind of ecosystem is exactly how Boeing and Airbus built their dominance in the first place, and it is what China has been trying to replicate. For Boeing and Airbus, the risk is not a sudden loss of global share. The C919 cannot compete worldwide until it secures EASA or FAA validation, and that will take years. The real concern is what comes next. If China proves it can build a working engine, the second version will be better, the third will be stronger, and the fourth may reach the efficiency levels that once seemed out of reach. A working CJ1000A also removes the last lever the West can use to slow the C919. Without engine controls, export pauses lose their force. Political pressure weakens, and China gains the freedom to move at its own pace, which is exactly what has allowed it to dominate other industries before this one. This is why the latest test results triggered such a reaction. They show an engine that works well enough to keep advancing. And once an engine program reaches that stage, the rest becomes a matter of time, funding, and iteration. China has both. The latest engine test did not deliver a headline that beats the LEAP. They delivered something harder to ignore. A working core, stable thrust, clean response, and flight hours that point toward real progress instead of early failure. That is why the mood shifted. China has crossed the stage most engine programs struggle with. The engine works, it flies, and it keeps moving forward. The open question now is simple. If this early version already looks this stable, what happens when China rolls out the upgraded models that are being built behind closed doors?